Okay, anytime I'm given a number of variables, I always want to make sure I understand what each of the variables mean. So when I look through here and I see calculating exponential growth, I look to see each of the variables where I see n equals n0 ERT. I'm familiar with this equation, and I'm probably thinking that what they mean is n equals, and I'm probably going to write it nt equals n, not e to the rt. As I'm familiar with this version of the equation, I'm pretty sure that's what they mean when they write this kind of notation. Different softwares have limitations on superscripts and subscripts. Now you can see R is the growth rate as a decimal, and where in the book it likes to say K, and then it says K equals R divided by 100. That's just saying that R is the growth rate as a decimal. So you have to take any percentage and change it into a decimal. All right, so T equals time, and E equals EX, and I'm assuming that means E to the exponent, right? The natural number. That EX, not something I'm familiar with. N equals the future population size, which is why I like to write an N to the T, because it lets me know there's some time in the future. N naught is the current population size, or the beginning population size, or the population size at N0. That's the way I like to think of it. At T equals 0, that's the population time. That's now, or it's your beginning population. And T equals I over R, the natural log of N over N naught. Now, where do they get this? Well, they just solve for T. And if you remember correctly from the last time we went through this, and I hate to take us through this again, but in order to get this RT, this value here, out from the exponent, we have to take the natural log of both sides. Before we do that, we have to get this term here by itself, right? And so to do that, we have to take nt and divide it by n naught. That's where they get n divided by n naught. Let me go ahead and put nt here, and there's an nt here. It helps me out. I hope it doesn't confuse you. So when we look at this and we get n0 nt divided by n naught equals e to the rt power, if we take the natural log, allow me to erase this here. Oops. N naught, and then that means natural log of nt over n naught equals the natural log of e to the rt power, which, as I tried to explain to you before with logs and natural logs, that means it's the natural log of nt over n naught, which equals r times t. Now, if I take then and divide by r to get rid of the r on this side, let me cancel out, as you see here, then what I see is that I have the natural log of nt over n naught over r equals t. Now you see what they wrote here in this equation is they just said they multiply times 1 over r, which I hope you know, as I said before, is the same as dividing by r. It's just another way of writing it. It's also, if you think of r as being r over 1, then if you're going to inverse and multiply, you would know that it's 1 over r. Several ways to look at this, but no matter how you look at it, the math is pretty straightforward. and that equals t. And that's actually exactly what you have here at this stage. So I'm not too worried about this. Seems like a fairly familiar oops. Yeah, do that. A fairly familiar equation, and I think we've done this I don't know how many times now, so I don't see, if you have a problem with it still, why don't we get together and talk about it, because this calculation is something we've done several times. There's absolutely no reason why everyone that's watching this shouldn't be able to do it. In any case, you have here your equation, the equation that they give you here in the problem set. Okay, so moving on. It says where r equals the growth rate, so this is the growth rate here, and ln is a natural log, and n is a future population, and 0 is the current population. Now remember, this is how we got that 70 divided by r is equal to doubling time, because doubling time when doubling time means the time the population doubles, the time it takes the population double. And so you have nt, and this is nt here. So nt would be twice n, so the ratio is 2 to 1. Natural log of 2 is 0.69. And if you divide 0.69, we'll round it off first to 0.7, and then divide by a percentage, let's say 20%, you invert multiply, that 0.7 turns into 70, and then 70 divided whatever that percentage was. Okay, so let's get rid of all this and start doing problems. And you see, I like to do this first. I don't like to just kind of guess it out or work through it first and then come back to the formulas that I'm given. It's so much easier if you go ahead and take the time to make sure you understand all the variables and all the equations. Okay, and problem number 1, it says calculate the doubling time for each of the following populations. In population A, for problem 1, it says it has an intrinsic rate of 4.4%. So R equals 4.4%. Now if it's 4.4% and we have and they want to know what the doubling time is. Well, this is pretty straightforward. So your time it takes to double your population is equal to 70 divided by 4.4. Now the rule is it's 70 if it's 4.4%, and if it's 7, it's 0.44. Well, I just keep making a mistake with these, so make sure you don't make those mistakes. So make sure that you have the 70 correct, and it's 70 divided by 4.4, and that's going to equal 15. Doubling time equals 15.9 years. You have to assume years. It doesn't say years. It's a mistake. But I like this problem set because it asks you to repeat in different ways to do the same kind of information, the same kind of question. And that's really important, is to practice the different ways someone might ask you a question. So that was for population A, and then population B, and they ask you which has 1,500 births and 800 deaths, and you have to find the doubling time. And of course, you're going to go ahead and do 1,500, right? 1,500 births minus 800 deaths, right? And that's going to give you the population change over 100,000. And if you do the math, equals 0.007. Now that's 0.007, but if we want to use the 70 rule, we could take 7 and divide it by 0.007, or we can take 70. Now we can go ahead and multiply by 100%, and that'll give you 0.7%. Okay, and at that point, now you know your growth rate. That's your R, and the question is, how long will it take to double? Well, your R is 0.7%, so then that would your doubling time again would be 70 divided by 0.7%, right? And so your R is 70 divided by 0.7. 70 divided by 0.7. Take you 100 years. Right? And finally, population C, it has a birth rate of 5%, and then you have a death rate of 2%. This is 5% minus 2%. That equals 3% total. Right? And then if you're going to go ahead and do doubling time doubled equals 70 divided by 3%, right? So if you take a look at 70 divided by 3% versus 70 divided by 0.7 versus 70 divided by 4.4, the smaller the number below the 70, the longer it's going to take. So you see here, when you divide 70 by 3, you get 23.33, and it goes on, but we'll go ahead and stop at 23.33 years, where here you have 100 years and here only 15.9. So the larger your percent are, the faster your population doubles, which makes sense, since the higher your growth rate, the faster your population is going to double. So that's just logic. It just makes sense logically as well as mathematically. And it should always make sense logically if it makes sense mathematically. All right. Okay, so 18, 30, and 41 seconds, Rob. And let's go ahead and read the problem. A colony of termites has an intrinsic growth rate of 150 per 1,000 in the population per year. Finally, they give us a time per year. So, and then it has a mound that occupies 0.5 square meters, starting with 10,000 termites, and assuming no environmental resistance. What is the size of the colony at the end of 3 years? What will be the area occupied by the termite mound in about 3 years? Well, aren't they a little bit tricky in this one? All right, so we start off with intrinsic growth rate of 150 per year and 1,000 in the population. So N naught equals 150. Oh, I'm sorry, 150 per 1,000. So that was not N naught. That's 150 for every 1,000. And your N naught is 10,000 termites. All right. Okay, so they tell you that R is equal to this, and they trick you they try to, in my opinion, they try to trick you by giving you this per 1,000. And it's not really a trick. It's just they tell you it's 150 for every 1,000. So that's your percentage, all right? And if you just take 150 divided by 1,000, it gives you the decimal version of the percent. So it's 0.15, which would be 15%, right? Just the way they word it is tricky. If we take a look at the next part, it says the mound occupies 0.5 square meters. All right, so it's really, if that is the N naught, but they give you kind of another ratio. They give you it's 0.5 meters squared for every 10,000 termites. Right, so that's actually a conversion factor. So when they ask you for how many meters later in the problem, you can calculate it. Well, if your N naught is 10,000 termites and your growth rate is 150 or 0.15, and you want to know what size is the colony after 3 years, well, you have most of your variables. So let's go ahead and take a look at how you would do this. So your formula is NT equals N naught times ERT. They give you T. They give you T is equal to, let's write down what we're given. This is kind of a problem solving 101. We're given our time, which is 3 years. We're given R, which is equal to 0.15. And we're given N naught, which is 10,000. And then they want to know what is NT. What's the population after 3 years? So all we have to do is just take NT. There's no algebraic manipulation really required here. Times 10,000 times E, R is 0.15, times T of 3. So you're going to take E to the 0.15 times 3, right? So 0.15 times 3 is 0.45. So that's 10,000. E to the 0.45 power. Now here again, taking natural logs, I don't think they're going to give you a problem like this, but it really is good practice to do it. Okay. So then you would take E to the 0.45 power. So on your calculator, it says in ln, which is natural log. That's what we had used before. But we're not taking natural log now. We're taking e to some exponent. So another button you have on your calculator is e to the x. And depending on how your calculator works, you would say e to the 0.45 power. And that equals, in this case, times 1.57, right? The actual number is 1.568, not 1.568312185490169, but 1.57 is good enough. Times 10,000 equals 15,683.12. All right. So this is our population after 3 years if we had a starting population of 10,000 termites. Given everything we've been given in the problem set, which is here, we have 15,683.12 termites at the end of 3 years. Now, how many square meters would their termite hill take up? Well, this is just dimensional analysis. It goes back to dimensional analysis over and over and over again. So going back to dimensional analysis, let's just go ahead and do it up here. So if I take then what I've been given, and that's that I have this many termites, and please note that I was a little lax. I didn't put the unit termite here. These are 10,000 termites. 1.57 has no units, but 10,000 is 15,000, or is rather 10,000 termites. So when I multiply them, it's 15,683.12 termites. So when I go ahead and put it into the equation to try to figure out how many meters I have to consider that what I want is meters squared. That's what I want ultimately. So whatever I do, I want to cancel out termites. I like to work backwards. This might confuse you, but I already know what I've been given, and something you should always remember, what you know. What is it that you know? You know 15,683 termites, and you know the conversion of 0.5 meters squared per 10,000. So if you take and you put meters squared on top, because that's what you want, it's 0.5 meters squared. And you know you have 10,000 termites. And what you're trying to do is get rid of 10,000 termites, or get rid of termites, so that you can have meters squared all by itself. What are you going to multiply by? Well, you're going to multiply by your 15,683.12 termites. And you know what? I'm going to write it smaller just so that it works out. Nobody gets confused. 15,683.12 termites. I'm going to put term, if you don't mind, over 1. See, now I know that termites cancel out. There's my dimensional analysis. And the only unit I have left is this wonderful little meter squared, which is my unit of area. And it's a really nice check that I'm looking for area, and I end up with area in my formula. So then when I take 0.5 and multiply it by 15,683.12, and yes, I'm using a calculator, I end up with 0.78 meters squared. Now this is my answer, 0.78 meters squared, once I canceled everything out. And it doesn't matter if you multiply 0.5 times 15,000 and divide by 10,000, or you divide 15,000 by 10,000 first. It really doesn't matter. The order of operations works out to be the same. But when you look at 0.78 meters squared, and you ask yourself, well, is this right? Is this reasonable? And this is always a question I ask myself when I do these word problems. Is 0.78 meters squared reasonable? I look back at what it was, 0.5, and I ask myself, did the population grow? Yes. So did I expect the termite mound to grow? I certainly did. Did it grow? It sure did. It went from 0.5 to 0.78. 0.78 is bigger. It's not much bigger, but then again, the population size isn't that much bigger. So my checks all seem to work out. My units work out. My answer is reasonable in 2 different ways. I'm pretty confident that this answer is correct. Now let's go on to number 3. I know this is taking a while, so you could stop now. You could have stopped after the first one and come back and look at each one individually. You could skim through and just check the work. That's why I try to write out everything as we go. Whatever works best for you. But I just want to make sure I cover all the bases with these problems. We're in a half hour into this, and we're on question number 3, a little more than halfway through. At the end of 1996, the population numbers 100,000. I'm assuming a population number 100,000. A population numbered, I believe they wanted to write. So the population numbered 100,000. So now I'm going to write down what I know. 1996, the population was 100,000. So N0 was equal to 100,000 in 1996. The next, you know what, let me write that neater. Let me write that a little neater and write it in black. So 1996, try to write it neater and it still messes it up. 1996, and I go ahead and we say the population, and let's not write in 0 or T yet because we don't know what the problem is. 100,000. And I know this is a population problem, so I know N is a population. The next year, there are 1,000 births and 800 deaths, 600 immigrants, and 900 emigrants. Okay, well, they're just throwing a few zingers into you. All right, so they're saying to you that we have to add up all our pluses and minuses, and remember that our growth, our rate of change, right, R is going to be equal to birth minus deaths. But that's not all. What else? It really, let's break this down. It really isn't birth minus deaths, is it? Really, R is equal to how many coming in minus how many are going out divided by the total population, right? That's really what we're talking about, isn't it? If you remember back to our systems thinking, if we have this system and we want to know what's the change in growth in that system, it's what's coming in, the pluses and the minuses, and taking some kind of total of that and dividing it by the total population you began with, right? So what are the ins? What are the things? Well, obviously birth is a plus, right? That makes sense. As common sense as sense can be common. And so we have birth, right? And then we're going to have immigrants. Those are people coming in. Immigrants in. I know that's an M, but it does mean in. People coming into a population are called immigrants. Those are the pluses. Minus the negatives of the people going out. And of course, one hard way of going out is death. An easier way of going out is emigration, or just moving, leaving without dying. So, and really that's all there is to that, right? And then divided by the total population. Well, if we get so we started with 100,000. That was the total population. Then we had some births, we had some immigration, we had some. That should have been a plus. Shoot, I should put a plus there. Make sure you know that that's a plus. So the births plus the immigrants minus the deaths minus plus the immigrants, right? So the total things going out and total people coming in, total people going out and total people coming in, divided by the 100,000, because that's how many you started with. That's going to give you your rate of change, right? So let's do the math. So we know that there were 1,000 births. We know that there were 800 deaths. Oops. Let's go ahead and put this over here. 800. And there were 600 immigrants. And there were 900 emigrants divided by 100,000, right? What was the total change in the population then? All right, so if we look at that would be 1,600 minus 1,700 divided by 100,000. Oh, look at this. And if we take a look at what that number equals, trying to use a calculator as little as possible, that should equal negative 100 divided by 100,000. And see, this is the kind of calculation they could ask you without a calculator, right? So now you have to know how many times do you have to move the decimal, and now that I have to move the decimal that many times, what is in knowing that it's a negative number as well. Well, there's a quick and dirty way of doing this. It's kind of I like to use it. It's a good rule of thumb. I can cancel out these zeros. And what that leaves me with, just trust me that it works. If you don't want to trust me, we can discuss the math. It's 1 over 1,000. Now, to me, that makes life a lot easier. So that little trick right there just made my life a lot easier. So it's 1 over 1,000. And I know that 1,000, I need to move the decimal 3.3 places. So 1, 2, 3. My placeholders, 0.001. So I know that when I take and I divide 100 divided by 100,000, that's going to equal 0.001. But of course it's negative 0.001. Now that's a decimal. If I wanted to make it a percent, then I would multiply it by 100, and it would be 0.1%, right? So the change is going to be 0.1%. So what's how did the population, how did the population change? Well, it changed at 0.001 in a negative direction, so that means it lost, right? It lost 100 people. Now, that makes sense if you think about it, because what you know is that you know how many people you lost. It's right here, this number. You lost 100 people. This just tells you the growth rate, right? So I calculated the growth rate. I really didn't need to. I just had to do this calculation here. But it was nice to do it because it showed you that you could cancel out these numbers. And there may be, I say probably because I haven't read ahead, but they might ask you for the growth rate. So what is the population size at the end of 1997? Well, it's 100,000 minus 100, right? So it's 100,000 minus 100. And you could do the math on that yourself, but I'll go ahead and say where is this? Where do I put it? It's going to be 99,900, right? And the birth rate and death rate in 1997, well, the birth rate is going to be, the birth rate was 1,000 divided by per 100,000, right? So it's 1,000 divided by 100,000, and that's 0.01 in decimal format. And so that would be 0.01 in decimal format, or 1% is the birth rate. Does that make sense? How did I do that? I just took how many people were born, which was what? Which was 1,000, and I divided by the total population of 100. So again, I just took, the question was birth rate. So let me quickly write in here the answer of 99,900. And as far as birth rate is concerned, and birth rate, any kind of rate is whatever divided by the total. And in this case, it's 1,000 divided by 100,000. And if we do 1,000 divided by 100,000, right? You know, if you take 1,000 and you divide it by 100,000, it equals 0.01. Or if I wanted to write in percentages, it'd be 1%, right? So that's a 1% birth rate. So what's the growth rate of this what was the growth rate of this population? Ha ha ha. I already calculated it. You saw me do it. And so let's just go ahead and put 1% over here. And then what's the growth rate of this population? It's negative 0.001. Or if I wanted to put it in percentages, it's negative 0.1%. If growth continues in at the rate 1997 rate, when will this population double? Well, if it continues at this rate, never. It's getting smaller, right? And if you look at it, it's 800. You have 800 deaths and 900. That's 8 and 900 is 1,700. 1,600. That's 1,600. Obviously, you're losing more than you're getting, so it will never double, and that's an easy one. But if it were a plus 0.1%, what would it be? It would be 70 divided by 0.1, right? So if it were a positive growth rate for whatever reason, if there were more people coming in than were leaving, then you would do 0.01 divided by, it would be your 0.001, 70 divided by your 0.001, which would be about 70,000 years, assuming it's 0.001 per year, and it would be in this problem. So a really, really long time. Okay, but again, that's assuming that the population growth was positive, but it isn't. It's negative, so it'll never double if this population rate did not change. All right, this is 44 minutes and 27 seconds, and now we're going ahead and moving on to problem 4. And it says Paraguay has a natural rate of increase. Natural rate of increase. Just another way of saying population change, right? Rate of population change. It's, they try very hard in this problem set to give you an idea of the different ways the problem could be stated. So in that sense, it's good. What bothers me is the lack of details, like not putting per year, or leaving some of the essentials out that might give you, if it were a real problem, might give you a clue or would give you some context in which to try to answer the questions. There's some assumptions you have to make as you're reading, and you have to be comfortable making assumptions, and that's something that not a lot of people are comfortable doing, and as well they shouldn't be. So this really shouldn't be stated so ambiguously. However, that's what we have to work with. So let's take a look at this. if you are in Paraguay, right, it has a natural rate of increase of 2.7%. If it's year 2000 and the population is 5.5 million people, what is its population? What will be its population in 7 years? Obviously, the person who wrote it quickly. I appreciate the work, so I'm not going to complain. I just want you to understand that normally a problem wouldn't be written so poorly as far as its grammar, and its meaning would be a lot clearer. But it's good that, again, the way they're stating it, the ambiguity makes you think it's a challenge. Okay. So again, it's 2.7%. R is 2.7. The year is 2000, so the beginning time is 2000, and the population is 5.5 million people. So let's write down what we know. R equals 2.7%, and so therefore it equals 0.027, right? And what else do we know? We know that in the year 2000, the population is 5.5 million. So when at 2000 equals 0.5 million. And then it says, what will it be its population 7 years? That's question one. And let's go ahead and figure that out really quickly. And it should be really quickly at this point, right? So in 7 years, so some n at some time. So n 2000 is really what? It's the beginning, right? So it's n0 or n0, right? This n0 is at 0 time. And 0 time is the year 2000 according to this problem. How did I know that? Because it's our beginning. So whenever you read something like this, it tells you this is the beginning. And the beginning means it's n0. Or in physics or in physical science, in physics we also use n0 or whatever not. Also, then another substitute for it that I think would have seen in physical science or physics is n initial, right? Remember, final minus initial. Well, this is the n0. It's the beginning. So in any case, the n0 is 2000 and 2000, and that's 5.5 million. And we know that it's t equals 7 years, right? So then the equation we know also is that nt, which is equal to n0 times e to the rt. And we know it's n7 because that's how many years, t equals 7. We know n0 is 5.5 million. And we know it's E, and R is 0.027, and time is 7 years. Right? So again, here we have to use the e to the x. We're not going to use the natural log. We're going to use e to the x. First, we have to get... we don't have to actually move anything. There's no algebraic manipulation at all in this problem. It's going to be 5.5 million, and it's going to be, what we're going to do is we're going to take e to the x. Well, first we're going to figure out 0.027 times 7 years, and that equals 0.189. And so this equals, I'm going to do it step by step, 5 million. And it's e to 0.189. And if you take e to the x, 0.189, that equals 5.5 million times 1.2 1. And if you wanted to keep significant digits, then 1.210. And then multiply that times 5.5. And that's equal to 6.644 million. Of course, that's years. That's years. All right. Oh, what am I saying? Years. Jeez. It is not years. I apologize. Million people in this case. All right. When will we achieve the population equivalent to New York City metro area of 20 million people? Ah, yes. He's thought of, or he or she has thought of a lot of different ways of asking this question. All right. So it's just another derivation of using the same old formula. There shouldn't be any kind of question. So the n at whatever time we're looking at is 20 million, right? We know what the n naught are, the n t is 20 million. We know the n naught is 6.644 million, right? And we know that that's multiplied times e to the r, which is 0.027 times t. Now we're going to have to use the natural log. So what we have to do in this situation is pulling out the calculator, of course, and it's going to be 20 million divided by 6.644, and that's equal to 3.010 million. Million is canceled, right? Because it's 20 million divided by 6.644 million, so they're canceled. So that's equal to what? 3.010 is equal to e to the 0.027 point t. So now we take the natural log of both sides. And if we take the natural log of 3.010, it is 1.102, and that's equal to the natural log of e is its exponent, and this is the exponent, so it's 0.027 times t. Divide both sides by 1.0. So divide 1.102 divided by 0.027, and that number is 40.815, and that would be years, right? Theoretically, time. Although the t is not, there's no years in this, but in any case, you don't see the unit years, but it's assumed because of time, and it tells you that the rate is actually 0.027. Should tell you something. The context tells you it's years. All right, so it's 40.815 years it would take to reach the population of New York if it continued at a rate of 0.027 or 2.7%. All right. All right, so that's it for problem 4. Now we're in the last problem. It's an hour later. Number 5, we're going to go ahead and start with what we know. And it says the World Bank says that DACA It says Dhaka, DHAKA, with its current 2012 population of 15 million, has a current 2012 population. So let me do, you know what, instead of writing it that way, why don't we go ahead and write the population N of 2012 is 15 million. I'm just writing down what I know. Always good to write down what you know. And it bears a distinction of being the fastest growing, blah, blah, blah. Between 1990 and 2005, the city doubled in size. So 1990, 2005 minus 1990 equals the doubling time, right? So the time doubled, and that equals a doubling time of 15. So that's 15 years to double the population of Dhaka. So there's a lot of information so far. And then it says, and the city between it doubled in size from 6 million. So in 1990, the population in 1990 was equal to 6 million, and the population in 2005 equaled 12 million. All right. And in the UN predicts Dhaka will be home to more than 21 million people. In 2025, they think it's going to be close to 21 million people in Dhaka, and bigger than any other of the bigger cities. So if we take all this, okay, if we take all this and we just kind of pull it down here, is information we know we're going to keep and stored in a corner of our paper. This is all information we know about Dhaka. And we go ahead and we start to try to answer these questions. And the first question that they ask here is, what was Dhaka's growth rate between 1990 and 2005? Before I even get there, there's a lot of calculations that you could do with this information. There's a lot of different questions they can ask you because they give you a lot of information here. So I just want to mention that. So if in Dhaka they ask what was the growth rate between 1990 and 2005? Well, we know that the growth rate equation, you get NT, the final would be 2005, right? And that's going to be equal to N naught, which is going to be 1990. And that's going to be multiplied times ERT. And we're going to go ahead and move it over, and we're going to get, algebraically, we're going to get N 2005 divided by 1990 equals ERT. And if we know what R is, and we know what the two N's are, we should be able to get T. And if we know what the T is, and we know what the N's are, we should be able to get R. And we're looking for the growth rate. This is the variable we're looking for here, right? The time we have, we calculated it already, actually, right? The time we know is 15 years, right? So because we know it's 2005 minus 1990, so that's 15 years. That's the time it took to double the population. We know that. And we know the beginning population of 2005 was 21 million. Oops, that's a mistake. That's not the beginning population, it's the end population, 21 million. And the beginning population was 1990, 6 million. And we know that that equals E to the R times 15 years, right? And we know that 21 divided by 6 is 3.5. That's a calculation we can do in our algebra, with our long division. Shouldn't need a calculator for that. Equals ERT. Now to get this down, we're going to go ahead and use our natural log. Right? Now we'll need a calculator if we're going to have to do natural log. The natural log of 3.5 is 1.25. And that's going to be equal to, now remember the natural log of our ER 15 years is the exponent, right? So R 15 years. Again, that's just a factor of the exponents. So 1.25 divided by 15 is equal to 0.083. That's what R equals. So there's our R value. So here what it asks you was DACA's R value or growth rate between 1990 and 2005. That's 0.083. Now what is DACA's growth rate from 2012 to 2025? Now they're asking you to take this this information that's more an estimate than anything else and make some calculations with it. So now for B, you have to take your 2012 and 2025 data. And you look at 2012, where is that data? That data is here, 2012. And your 2025 is here. We're still using the same equation. We're still going to go ahead and say, N T equals N naught times E to the RT. And NT is equal to 2025. So that's 21 million. And then naught is 15 million. And you see it's exactly the same calculation. ERT. And what's the growth rate? We're looking for R. And the time difference between 25 and 12 is 13. So the time difference here is 13. So we have 21 million divided by 15 million equals ER times 13 instead of 15, right? Now we're going to need that natural log again because we're actually pulling the number down. But we're going to go ahead and do the math. 21 divided by 15. That's 1.4. Again, a number we could calculate without the need of a calculator if we had to. ER times 13. We take the natural log of both sides. Natural log of 14, you'll need the calculator for that, is 0.336. And that equals RT. Why does it equal RT? Because the natural log of E to anything is that exponent. That what I just underlined is the exponent, all right? So that comes down to this spot here. E goes away. So now we have to divide both sides by 13. So 0.336 divided by 13 Probably best done with a calculator just for time's sake on a test, so they probably won't give you something like this. As far as the numbers, I'd assume that they might give you a question like it, but they'll simplify the numbers so that you don't need a calculator per se. You're still going to have to do long division. 0, 2, 6 equals R. So R is 0.026. So Arthur, the growth rate here is 0.026, or if you multiply times 100, it is 2.6%. And up here in the previous problem, it was 0.083, so it would be 0.083